Welcome to Puzzles to Exercise the Mind, lesson number 12. We have a few more high school algebra type problems at the beginning of this lesson, and then we have some other puzzles that follow after that. So for our first puzzle, this is something you might see in high school algebra. That's not to say it's easy. These are, I find them rather hard to translate into equations that you can solve. So let's look at this first one. We're given 20 liquid ounces of a 20% vinegar, 80% water solution. How much vinegar should be added to make the solution 25% vinegar and 75% water? So you may want to pause here. I'll give you the solution on the next slide. I've copied the problem here at the bottom. Use the pointers just so we have it to look at in case we need to check. So let X be the amount of vinegar added to the solution. In other words, how much we need to add. And note that we already have 20% of 20 liquid ounces. So we have 4 ounces of vinegar. And we want the amount of vinegar, X plus 4, we don't know what X is yet, to be 25% of the total volume, which is now 20 plus X. So we've added X ounces of vinegar, so the total volume is changed. And that's the trick. That's a little bit of the complication in the puzzle that you could easily miss. So our X plus 4, the amount of vinegar after we've added some vinegar, we want that to be 25% of the total amount of liquid, which is 20 plus X, which X is all vinegar, but that's okay. So this is the equation. And once you have this, it's pretty easy to solve it. You just take 0.25 times 20 and times X, and you get 0.25X, and a quarter of 20 is 5. Then you subtract 0.25X from this side, subtract the 4 from this side. You get this equation, then you divide, and you get 1.33 going off to infinity. This little bar means that the 3's are repeating infinitely. Okay, so that's our solution, and I have another one similar to this, a little bit harder on the next slide. So the next puzzle is basically doing the puzzle we just looked at, but in reverse. So assume that we have a liquid consisting of 21 1/3 ounces, and 25% of that is vinegar and the rest is water. And we want to know how much vinegar to extract to get a mixture down to 20% vinegar. I realize that's, chemically that might be a difficult thing to do, but just looking at this logically, let's figure out how to do that, assuming we can extract vinegar without removing any water. Okay, so I'll give you the answer on the next slide. You may want to pause here. We let X be the amount of vinegar to be extracted from the solution. And note that we start with 0.25 times 64/3, or 1/4 times 64/3, or 16/3 ounces of vinegar. And then the other amount is the water. We're being asked to determine how much vinegar to extract such that the resulting solution is 20% vinegar. So we can represent that with this equation here. So we're subtracting the X amount of vinegar, we let X be the amount we're removing, from the amount of vinegar that we started with in this particular problem. And we want that to be 20% of the total amount of liquid. So the total amount of liquid is 64/3 minus the X ounces of vinegar that we remove. And then this last thing on the right is just multiplying through. So, or not even multiplying through, just converting 0.2 to 1/5. So we have this here. So let's focus on this and not the middle term. We have a common denominator of 15 across here. So let's multiply both sides by 15. And this will give us 80 minus 15x. And then 15 multiplied here, this 5 goes into 15, 3. So that'll be 64 minus 3x. And then it's pretty easy from here. You add the 15x to both sides, and you're going to get 12x on one side, and then subtract 64 from the 80, and then divide 12 into 16, and we get x equals 1.333 out, an indefinite number of threes. So that verifies kind of what we did in the our solution to the first problem. Okay, so we have a few more of these. Hopefully you'll get the hang of it after we look at a few of them. Well, this one's a bit harder than the first two. Car's fuel tank has a capacity of 20 gallons. The completely filled tank currently contains a mixture of 85% gasoline and 15% ethanol. How many gallons must be replaced? So we need to take gallons out of the tank by a 55% gasoline, 45% ethanol solution to result in a full tank of 20 gallons of 70% gasoline and 30% ethanol. I'll give you the solution on the next slide, so you can pause here if you want to give it a try. Probably the hardest part of solving this puzzle is actually figuring out what to label x, the unknown. That's generally true in these type of puzzles. So I don't mean to make light of this, because it's easy to just state let x be this, and then everything kind of follows easily. But I think this first sentence is probably the hardest part of the problem. So let x be the amount of fuel removed from the starting mixture. That is what we were asked. And by the way, I copied the question down here on the bottom in case you need to look at that as we talk through it. So the problem is to determine x from the given information. If we remove x amount from the original fuel, then 0.15x of ethanol has been removed, since the solution was 15% ethanol. And by adding an amount x of the new mixture, we add 0.45 times x ethanol. That's because the new mixture is 45% ethanol. We want the resulting mixture to have 6 gallons of ethanol. So I wrote everything down here in the table, which I hopefully will help. So originally we have 15% ethanol, and that's 15% of 20 gallons. So we have 3 gallons of ethanol to start with, and we want to remove 15.15 times x, let's say. So that's how much we remove. X is the amount of fuel that we remove, and 15% of that is ethanol. So we're removing minus 0.15x, and then we're adding plus 0.45x, because that's the percentage of ethanol in the new solution. And we want that to equal 30% or 6 gallons of ethanol. So we have this 3 minus this plus this equals 6. That's the equation we need to solve. And we'll do that on the next slide. This equation here comes from the bottom row in the table we had on the last slide. You recall we had 3 minus 0.15x plus 0.45x equals 6. We just subtract the 0.15 from the 0.45 and get 0.3x. We get this equation. Then we subtract 3 from this side and we get this. And then we divide by 0.3 and we get our solution. So we need to remove x gallons from the original solution and replace it with x gallons of the new solution in order to get a solution with 30% ethanol. We can check that here. On the bottom I have a table. So if we remove 10 gallons of the original mixture, that means we're removing 1.5 gallons of ethanol. Then the amount of ethanol from the 10-gallon added to the tank is 4.5. So the total amount of ethanol after we've made this switch here is the 3 minus 1.5. So this was the original amount minus the 1.5 we removed, and then plus the 4.5 that we added, and that adds to 6, which is what we wanted. We wanted the final solution of the in the gasoline tank to be 30% of 20 being ethanol, and that's what we got here. We have one more of these mixture type problems. We have two mixtures of coffee. Coffee mixture A is 10% cream, and coffee mixture B is 20% cream. And let's assume we have a lot of these. Let's say we have 100 liters of each, so we're not going to run out of either in order to make what's being asked in this problem, which is how many liters of each solution should be used to make 20 liters of a coffee mixture, which is 15% cream. And I'll give you a hint. Let X be the amount of coffee from mixture A. There's other ways of doing it, but this is my hint as to how I'm going to solve it on the next slide. So we have our solution here, or at least my version of the solution. And I copied the statement of the problem down here at the bottom in case you want to refer to it. So as I suggested, let X be the amount of coffee from mixture A. That makes it easier just to have one variable here. So then the amount of coffee used from mixture B is 20 minus X, since we're told the total amount is 20 liters when we mix these two things together. And we want to have the final mixture being 15% cream. So what we have is 10% cream from the amount from mixture A, and 20% cream from the amount of mixture B, and we want that to be 15% of the 20 liters that we end up with, so we want that to be 3. And then from here it's pretty easy. You just multiply out, so you get a 0.1 here and a minus 0.2x here, so you get a minus 0.1x. And then the 0.2 times the 20 is 4. You have 3 on this side. Then I mixed a few things together here. I subtracted the 3 from the 4 to get 1. I added this to the other side and then divided by 0.1 and you get 10. So we can check this. 10 liters of coffee mixture A and 10 liters of coffee mixture B yields 10 times 0.1, 10% basically, then 10 times 0.2, and again we're using an equal amount of each, that's why I have a 10 here, and then that gives us 1 plus 2 equals 3. And 3 liters of cream and a 20 liter mixture of coffee is the required 15%. This problem's a bit different from the first few problems we saw in this lesson. It involves a balancing scale. We saw an example of that in the previous lesson. This is another balancing scale problem. We want to find the minimum set of standard weights needed to balance any integer amount up to a given weight under the following conditions. And basically it's two different problems. In one case, the weights have to go on one pan of the scale, and the thing you want to weigh goes on the other pan. And then in the second version of the problem, you put the thing you want to weigh on one pan of the scale, but then you can put the weights both on the opposite pan, but you can also put some of the weights on the same pan as the thing you want to weigh, and that actually gives you more flexibility. In terms of history, recreational mathematician Rouse Ball attributed this problem to Bachet in the early 17th century. In other words, Bachet in the 17th century, not Ball. And it was called Bachet's weights problem. However, the problem can be traced back even further to Fibonacci in the year 1202, and so this makes the problem a viable candidate for the first problem in what's called integer partitions. So let me show you a picture of what I'm talking about here in case it's not clear, and I'll do that on the next slide. Okay, so here's the problem. Let me state it again with the picture now. So you want to figure out what set of weights you need. So some standard weights, let's say they're in ounces, and you want to be able to weigh some other object like chocolate, maybe a couple of eggs, some vegetables, something you're looking to weigh, maybe a postal letter, and you want to be able to weigh all integer weights up to a given weight. So if you say 10, you want to be able to weigh everything up to 10 ounces. What's the minimum number of smaller weights, and what sizes do you need to do that? And the two parts to the problem. One part is you can only put the weights on one side. So you put your chocolate or whatever else you want to weigh on one pan, and then you try to balance it with these little weights until you get an exact balance. That's one problem. And then the problem actually has a different solution. If you can put the thing you want to weigh on one scale, and then you can put the weights, some here and some here, you can distribute them. That actually gives you more flexibility, and we'll see that we can get by with a fewer number of weights and weigh the same amount of stuff, whatever you want to put in the scale. Okay, so it's I'll give you the answer to the first question, where all the weights have to go on one side and the thing you're weighing on the other, on the next slide, and then I'll give you the answer to the second question on a subsequent slide. So as I said, we're going to look at the first question on this slide here. The weights can only be put in the free pan, and then whatever it is you're weighing goes on the other pan. So let's say you wanted to weigh everything up to 1 unit. We'll call it an ounce. I'm familiar with ounces, but it could be grams, it could be milligrams, whatever is of interest. But we'll talk about ounces here. So of course you just need the one integer weight. It's of weight 1, and that'll let you measure this. That's pretty easy. Now if you want to measure everything that's either 1 or 2 ounces, then you need 2 different weights, a weight of 1 and a weight of 2. Ignore this row for a second. Then if you have 3, well, we don't need to add anything more here because we could use the weights of size 1 and 2, and we can add them together. That's what I'm showing down here, and we'll get 3. And then for 4, we need another weight. There's no way we can balance 4 with just the 1 and 2. So we need to add 4, and then we could just use that weight to balance the 4, and anything less than that. Then if we have 5, if we want to be able to balance any weight up to 5, so in other words 1, 2, 3, 4, 5, we can still do that. We know how to do the lighter weights already. And then the 5, of course, is 4 plus 1. Then 6, we could still use the same 3 weights. It's just 4 plus 2, 7. We hit our limit, right? It's 4 plus 2 plus 1, and that'll give us 7. And then we need to add one more weight, and we'll make that of size 8, and that'll let us be able to balance any weight from 1 to 8. And then 9, it's just 8 plus 1, and you can see where this is going to go. It'll stop at 15. When we add 1 plus 2 plus 4 plus 8, we get 15, and then we'll need a weight of size 16 to get to the next level. So this row here, which I was ignoring, you notice this is just the binary representation of these numbers up here, but it kind of gives you an idea of how many weights you need. So if someone said, well, how many weights do I need to get up to 5? Then if you put it in binary, you can see that you need 3 weights, and it also tells you what the weights are that you need. You need the size 1, 2, and 4. So the general solution is to convert the largest amount of weight that you want to balance on the binary scale, as we have done here. So for example, 31, that's 1, 1, 1, 1, 1, 1, meaning we need weights 16, 8, 4, 2, and 1. And if it was something in between that, like 25, you would still have the 5-bit number here, and that would tell you would need 5 weights, basically these 5 weights. It's just that you would be able to measure more than the 25. So there's kind of these jump points where you need to add another weight. Now the problem is different when you could put the weights on both sides of the scale, and we'll see that. That's a little bit more involved, but you may want to give that a try given what we've done here, just by looking at the different weights that you need to go from 1 to whatever. And I'll give you the answer on the next couple of slides. In this version of the problem, we're allowed to put the standard weights on either side of the scale. And we have a table like we had in the previous version of the problem. We have the weights across the top, in other words, how much we want to weigh up to on the top row. And then we've written those numbers in base 3, or what's called ternary. So for example, 6 is 20 base 3. It's 2 times 3 to the first power plus 0 times 3 to the 0 power. In other words, 0 times 1 plus 2 times 3, and that's 6. And then the required weights are in the third row, and I'll explain those, but we're going to use powers of 3 rather than powers of 2 here. That'll allow us to get along further than what we did in the previous version of the problem. And then the fourth row here is the combination of the thing being weighed in black and then the standard weights in red, and the semicolon separates the left side and the right side of the scale. So for a weight of size 1, we just need a standard weight 1, and we measure it by putting 1 on each side of each pan. 2 is where it gets interesting. We're going to use 1 and 3 instead of 1 and 2. And we'll put a 1 and a 2 on one side, one pan, and 3 on the other, where the 2 again is the thing being weighed, and the 1 and 3 are the standard weights. So if it balances, that means this is exactly 2. 3 is easy enough. We just put the thing being weighed and the standard weight 3 on the other side. And we can also get up to 4. Remember, we couldn't get up to 4 in the other version of the problem. We had to add another weight. So that's the advantage of using 1 and 3 here. We can get one more weight with just 2 standard weights. We put 1 and 3 and 4. Then to get to 5, we need another weight. We could add a 5, but we can get much further by adding a standard weight of size 9. And you can see here 9 will balance with 5, 3, and 1, where 5 is the thing being weighed, and the red again are the standard weights. Then you can do 6, 9 on one side, 6 and 3 on the other. The thing being weighed is 6. The thing being weighed is 7 here, and then you have 10 and 10 on each side. You can do 8, same way. You have 8 and 1 here and 9 there, and if this balances, then 8 is exactly as we would expect. If it doesn't balance, then that means the 8 is wrong because we assume the standard weights are correct. Let's continue on the next slide, where we'll see the pattern more fully, and I'll explain how this works. But notice that when you hit 1, 1, that's sort of the break point. And when you hit 1, that's another break point. And we'll see where we have 1, 1, 1. That'll be another point where the next number after that you have to add another weight. And if you have 1, 1, 1, 1, in other words 4 ones, you would have to add another weight just after that ternary number. So let's look at a few more numbers here using just the weights 1, 3, and 9. 9 is easy. 10 isn't much harder. We use the standard weights 1 and 9 on one pan and 10 on the other. 11 is slightly tricky. We use the thing we want to weigh 11 and the standard weight 1 on one pan, and then 9 and 3 on the other pan, and that balances 12 on both sides. 12, a weight of size 12, we can balance with a 9 and a 3. And then the last one we can do is 13. We'll need to use all three of the standard weights on the other pan, and that'll balance 13. So we've gotten quite a bit further than we did in the first version of the problem with just 3 weights. Now we're stuck because we can't get any more than balance any more than 13. 14 weighs more than all 3 of these together, so we need to add one more. But again, we won't just add 14. We'll add the next power of 3, and you can see here we put the 27 here, and then our 14, 9, 3, and 1 from these standard weights on the other side, and that exactly balances 27. Then we could remove the 1 when we put in 15, and so this is still 27, and that'll balance with 27. And we can go up to the case where we have the sum of these, so it would be 27 and 13. So we can go up to 40 using just these 4 weights here. Okay, so it's kind of tricky. The reason we have the ternary here is an explanation of how we determine when we add the additional weight. And you can see here the cutoff point is when you have 1, 1, 1, or in the previous slide when you have 1, 1, and when we get up to 1, 1, 1, 1, in other words 4 ones, that's when you need to add another weight. So basically you take your weight, let's say it's 15, you write that in ternary, and then you see where that falls with respect to the 3 ones. If it's less than the 3 ones, in other words one of these numbers here, you can get by with just 3 weights, 3 to the 0, 3 to the 1, 3 to the cube. And if your number is bigger than the 1, 1, 1 in ternary, like 120, then you're going to need a 4th weight, and you'll be able to do that all the way up to you hit to the 1, 1, 1, 1. So pretty interesting problem. As I mentioned at the beginning, it's been around since, as far as we know, the year 1202, and you can imagine why it would be known for a long time, because we didn't have, of course, people didn't have electric scales then. They had balancing scales, and they actually did have little weights. So, if you wanted to mail a letter, or if you wanted to buy some spices or something from the food market, you would put that in one side of the scale, and then the person that's selling you the item would, pick some selection of standard weights and put those on the other side, and then you would see that, how much it is, and then you would decide on the cost from that. I have a couple of references for you. There's an article on something called ARXIV. I'm not sure if this is something pronounceable or not, but it's a website where people post articles, technical articles, typically math, physics, and the sciences, before they actually publish them in a more formal journal. And I guess the idea is they tell their colleagues that, I have a new idea and I'd like you to have a look at it before I try to publish it. And sometimes I guess problems will be found and it'll never get published, or maybe it's not interesting enough and it won't get published in a formal journal. But there's a lot of articles here. So this particular one by Mr. O'Shea is entitled Bachet's Problem at as few weights to weigh them all. That's the title. And I want to just highlight one theorem that he proved in this paper. He proves every integer weight L, with L between 0 and m, can be measured using a 2-scale balance with weights from the set 1, 3, 3 squared, 3 to the n minus 1, and then m minus the sum of these first numbers in the set. So this is just one number here, but it's a complicated number. So for 25, for example, just to give an example how to do this, we can measure all the numbers up to 25 using 1, 3, 9, and then this number here is 12. If you put in the 25 and then you add in the 1, 3, and 9 and subtract from it. So this is a little bit different from what I explained, because what I explained is taking, I would have said just take 3 to the, the next number here, 27, and that would give you more than 25, but you would have a heavier weight in that case. What O'Shea is saying is if you wanted to get exactly the weights you need to measure up to 25, this is what you would do. You would take powers of 3, and then the last weight would be this one here, 12. So you might want to try it for 57 or some number, and just to see what weights you need. And there's another place where you can read about this puzzle. This is a book by two people named Levitin, and it's called Algorithmic Puzzles. So the puzzles there tend to have algorithms, steps, processes, which you can see from what I explained. This is kind of a process that you go through to find a solution. And it's if you get the book, it's puzzle number 115. It's a pretty good book, so I would recommend it if you're interested in puzzles. Our next puzzle is known as Guarini's 6 Knights Problem. Guarini was a medieval mathematician in the 15th and 16th century, and he posed a number of chess problems. The one we have here, and I'll explain more on the next slide where I have a picture, but it's moving. You have 3 black knights from chessboard and 3 white knights, and you want to exchange their positions. And again, I'll show you what that looks like on the next slide. The solution is, or the minimum number of moves is 16, and that's proven in this book that I mentioned on the previous slide. In this case, it's puzzle number 118. There's also an online app. I have the link here that you can use to attempt to solve the puzzle. It'll track your moves. And in fact, I'll use that when I show you the solution. Okay, so we have the problem here visually. We have 3 white knights on one side of this reduced chessboard and 3 black knights on the other side. This is not a normal chessboard. It's restricted for the problem. And we want to, using legal chess moves, move the white knights to this side and the black knights to this side. So for those who are not familiar, let me show you how a knight can move. So let's look at the middle one here. So a knight can go 2 spaces up and either this way, or it can go 2 spaces up or that way. If we were on a bigger board, it could go 2 spaces that way and down this way, or it could go up. So basically, it can make an L-shape maneuver. That's the restriction. So you might want to use the online application that I referenced on the previous slide. I'll put the link in the information to this video. That'll make it easier for you to kind of move things around and track your movements. So here's the solution, and I've used this particular notation for the reduced chessboard that we saw on the previous slide. I just put numbers in here, 1 to 12, and so we started with the knights here and here, and then I have the moves listed here. So we go from 1, and there are other solutions, but it's the same number of moves, at least the minimum. So we can go from, this thing here says 1 to 6, 6 to 7, and then white would move and would go from 11 to 6, and then to 1. And remember, we move this one to here, so this is now open. And then the next move would be black, 3 to 4, 4 to 11. And again, we had moved the white piece out of there previously. So I won't go through all these, but if you use that online app that I mentioned, or if you make your own little chessboard and have the knights there, maybe on pieces of paper, or if you have more than one set of chess pieces, then you can kind of just do the experiment on a chessboard, and you can trace these steps, and you'll see that gives you the movement that we're looking for in exchanging the black and white knights on the board. I used the application that I mentioned to you 2 slides back to give you a sense of how the movements go. Basically what I showed on the last page. So you can see here we move the white first. Then we're going to move the black piece here, and then to the open spot. Now white goes next. Move it here, then down. So now we have a black piece and a white piece in the position we desire. And then move black here, and then here, and then there. So that put black in the right position. We're getting close to the solution. So white is here. Now we have 2 white and 2 black in the right spot. Move white there. You can probably see what's going to happen. 2 moves with black, and black gets into the right position. And then we have white. So we've exchanged all the pieces in the way we want it. We have a digit arrangement problem. The number we see here is created by concatenating the first 60 positive integers. The spaces are just for readability. You can think of this as just one number. And then we're asked to delete 100 digits. So you can delete 3, 6. You can delete the 1 from 10 if you like, or you can delete both the 1 and 0. These 2-digit numbers are just part of the stream now. You can delete them independently. But you have to delete 100 of them, and then you squish them back together, and you want what's left to be the smallest possible number. So you may want to pause here, and I'll come back on the same slide and give you the answer. Okay, so I'm back. The first thing we want to do is figure out how many digits there are altogether here. And we want to make sure there's 100 digits, so it's not even a trick question. And there is. We have 9 1-digit numbers, that's 9, and then we have 51 2-digit numbers. So we have 111 digits. We have to delete 100 of those to get the largest 11-digit number. So what we do is we delete all the digits from 1 to 50, leaving just the zeros. So we'll leave the 0 from 10, the 0 from 20, the 0 from 30, from 40, and 50. And then that'll give us 5 zeros in a row. So that's kind of reduced things down as small as we can get there. And then we have 51 to 60 left. And that's another 20 digits, and we have to get this whole thing down to 11. So I'm going to delete the 5 from 51, 5 from 52, and so on. And then the 5 from 55, and then delete all the other numbers beyond 55, and we'll still keep the 0 from 60, and that'll leave us with this number here. You may need to think through that a little bit to convince yourself that is the smallest number, but in fact that's the smallest number you can get using this process here. For this puzzle we use the same number that we had in the previous puzzle, the integers from 1 to 60 concatenated together. We also remove 100 digits. We're not allowed to rearrange, but in this case we want to find the largest number that we can create using that process. And we know it's going to be an 11-digit number. We did a calculation before. It's just what we delete now is going to be different. So you may want to pause here. I'll come back in a few seconds and I'll give you the answer on this slide. So as opposed to leaving zeros, we want to leave 9s here. And what we'll do is in the numbers from 1 to 49, we'll delete everything except the 9. So we'll leave 9, we'll leave the 9 from 19, the 9 from 29, 39, and 49, and we'll get 5 9s. And that'll leave us with 22 digits. And we need to remove 16 more in order to get down to our 11-digit solution. So what we do here is, let me show you the final answer here. What we want to do is, from the numbers 50 and above, we'll delete 50 to 56 altogether. Then we'll remove the 5 from 57 and the 5 from 58. That'll give us the 7 and 8 shown here. And then we'll be left with 59 and 60. We don't have any more deletions to use. And that'll give us the biggest number using this given process. So like the last one, you may need to think through this a little bit to convince yourself that's the best you can do. In fact, if you don't believe me, you can try to get a bigger number and you won't be able to. This is the optimal solution. Okay, so that's the last puzzle in this lesson. I have one more lesson that I prepared. I just need to record the audio and I'll put that up on YouTube. And if I get any suggestions for further lessons, I'll consider creating a few more. So feel free to comment, and thanks for listening.